Okay guys, please bear with me on this. I've did a little mock-up for you, a little model if you will. So this would be your, let me step into the camera a little bit. Okay. Maybe that lighting won't work at all, let's see. Yeah, that just might work just the same. Let's just do that. Let's just eliminate that lighting, go from there. Alright, what do we have? This would be the back of the structure. This is not the scale, but kind of proportional. I broke some of it off here with playing around, so bear with me. What I want to show you is that these will be like this 1 through 6, D1 and D1. This is what the OSHA report is showing, these cracks here, here, and here. I want you to think of this as a girder, the back of it as a girder only. And on that girder, I want you to think of number 12 sitting in the center of that girder with this bit of an anchor support, if you will, this extra bar as we look in the video. But this also goes up like that, so it's a lot. It's more, but I wanted to show it this format. But it goes all the way up like this, solidly. So it's this wide. I'm sorry. Yeah, this wide. Not just this, but I wanted to just focus on this, and then we'll add the weight back for it. When we look at it this way, I want you to see that there's the anchor point from the number 11. This would be B, I believe. There's two of them. There's an A and B anchor point. B being the only one of the post-tension rods that go through the diaphragm and holding, I say clamping, the clamping force, holding on number 12, and remember 12 again is the full length. So let's look at it like this. This is, again, not the scale, but kind of, you know, crazy close, like 30 degrees, and I didn't want to go crazy with it, but I just didn't want to. Here's, let's call this the deck. It's what I call anchor points here. Let me see if I can get us a little more lighting on that. Okay, let's try that. It's got a little shadowy, I'm sorry. So this is A. This is going down. This is going down A. Why did I have these separate like this? To help you understand that these were different pours, as OSHA reported, that the deck was poured with the diaphragm at the same time at the diaphragm. So if I were to put this on here and try to show it to you, the deck was poured in the diaphragm only, this lower part, this part, I believe, with a block, because of the paint colors, concrete colors. So I believe with this block, that's why I did the block thing also. And then the secondary uprights were poured and the diagonals. So I could not find a seam, but I can find separate coloring that appears to be a seam or bad formwork. But the coloring I just find too lucky, I don't find that they poured this and this at the same time. In other words, that they poured number 12 and this outside different coloration, because when we look into the video that I'll show you, this, and look into the corner, we see that this coloring is the same. So that's why I'm also doing this. So the diaphragm, I think, looks similar to this with this extension. That's what I'm extrapolating from my images at this time. So what was poured first was the deck, and the deck stops here. This is the deck. Going over, and you would see it would then include this little block, as I'm calling it. Next poured, I wish I could have found the other end, because I could prove that, because apparently they buried this number, this guy, when it was buried, this is the A, it was buried into the deck. We still see it in the deck in the images. We do not see B inside the deck, inside the diaphragm, because it doesn't exist. Doesn't exist there. It exists in the number 12 upright. So this would be number 12, and remember, this goes all the way up. Don't forget that. But it goes through what appears to be the first part of the pour here. What's holding this on? It's on top of the pier at this point, supported underneath my hand, if you will, the pier. So imagine if there was no pier there, and I remove. Well, let's talk about the clamp. I got to get back to that. So here's B. This is a clamp. I'm looking at it as a clamp coming through the diaphragm and holding number 12 to the back of the structure. And number 12, and it goes all the way down. Number 12, I'm specific about saying holding number 12. If I remove this block, so we can get a better clarity of things, again, this is where the cracks presented. There's nothing, and we look at the reinforcement in the OSHA report, the reinforcement is all vertical. Nothing horizontal besides right on the outside, apparently, and they didn't take apart the rest of the diaphragm. But what matters is where it peeled apart, where it slid off downwards, is that, and that would be looking at it from the top, if you will. That would be this load pushing this way towards this diaphragm. The diaphragm not being able to go down any further because the diaphragm is sitting on top of shims. As we know, I think it's 3 or 4, or maybe 1, 2, 3, and 4. I could stand corrected on that. But no shims in the middle. And this is what Denny Pate was saying. I had shims. I'm sorry, the grouting was supposed to be done part of the plans. And part of the meeting he had, he said, hey, it was supposed to be grouted. OSHA report states that MCM said that we thought we can grout at any time, as OSHA reported. So what's happening here, this is the dead load, this is dead weight, this column number 12. It's outside of the diaphragm. There's a huge part of it outside of the diaphragm. The diaphragm being here. The post-tension of number A, as I show you here, A in the number column 11, stops before it hits, or just barely clips inside 12 here, just barely clips it. It's not inside 12 in that capacity. 12 is the upright, right? The diagonal, the upright at the end of the structure, where the post-tensioning goes through the top of the member here, which I removed for reasons to show you about a joint. I want to show you at the top here how I can just do that. And I'll show you, and you can go back to the drawings and you'll see that there is just a joint. There's a joint there, and as reported by OSHA, the pores were first the deck, then the 12 and 1 through 12, which includes what I'm calling the upright and the diagonals, then the canopy, and then the blister bars. So these are your joints, and before you clamp them, they basically can do this. And once you clamp them, the clamp force will stop them from doing that. So we have a clamp force going through the blister bar here, the first blister bar in A and B, coming out, and we saw the failure of that. I need to bring this back up. At one point in the videos, when the bridge first failed, and we talked about, and I made a video about how the crane left. And I said, but interesting, the crane would have data on it, computer software, they need to grab that up, just to grab it up for a matter of record. Now, it's come home to roost, and with my extrapolation that would be great to use with OSHA's report, because if it has a computer record, it can show that they reported to OSHA, and OSHA reported in the report rather, that they increased the post-tensioning of this by going in 50s, 50 kips, 50 kips, 50 kips, 50 kips, back and forth. This revolution, if you will, of a cycling would show that the crane operator had to move the machine once, twice, once, twice, once, twice, back and forth, once cycling, to get to the maximum amount of kips. If the crane operator says, oh no, I only moved it twice, that means the report needs some correction and go after VSL for post-tensioning this without cycling it properly. I think that's VSL, right, that did the post-tensioning? Because that means they would have just loaded this in an imbalance, and that would couldn't create an issue too. Also, detensioning would create an imbalance. So detensioning matters too, how they detensioned. 1, 2, 1, 2, or did they just ratchet it out and then ratchet it out? Did they only move it once when they detensioned, and when they put it back on, did they only move it once, or did they really cycle it 50 kips at a time, or whatever the detensioning calls for also at 50 kips at a time? Perhaps it would stand to reason. What would the cycling effect have on the bottom of this structure here? I'm gonna, hopefully this video, maybe I'll tie it in with the, this will be part 1, and then I'll tie it in with part 2, talking about the same thing, showing, well, maybe I'll do a merge over, I don't know. The software is pain doing all this editing. So now, look what happens if I don't have any clamp force inside this diaphragm, and it's just connected by reinforcement. from here to deck to here. It's only, keep in mind, this is only here. This is, I've got it for scale, I have it as large as this. But I have a line going through here. And this is the true deck ratio, if you will. Not true deck ratio, but it helps you out. I just wrote anchor point here because now I'm going to remove what I call anchor point. I put a line through it, so hopefully it'll be nice. All right, so now I remove that. And now we get, yeah, let me get my knife. Now you see it now in more in scale. So now we're looking at more in scale deck. So anchor point is inside the deck only here. That's A. That one, releasing it, would only affect A and also the canopy loads, whatever downward force that clamp force would create. It would be a counterbalance inside here, helping with the cantilever, as we know. But what happens if I just, the cantilever is held on by what? If this anchor point is here, if this anchor point is here in the deck, and they transport it during transportation, the only thing holding on the outside here would be the connections, the reinforcement at the joint to the canopy, and the reinforcement from the deck, hold on, from the deck, transversing into the diaphragm. Then the only thing that's holding it in the air and anchored to this point is the clamping force of B only, Interesting, if you look at the post-tensioning scheduling, you'll see that apparently they're both equal. And yet clearly B would have been experiencing more forces because it's got this extra load on it. But again, depending on the development from here into here, perhaps you can get a nice secure joint. You'll still transfer the loads and balance, but outside of where just outside into the diaphragm. So here's our pipe, and the anchoring point is above the pipe. That's the drain pipe, if you will. If I remove this, we show it now in the diaphragm going through. If I leave this out and turn again, we have an anchor point outside of this diaphragm in the deck only. If you look at it, it's just barely, it's in line with 12. So this is the one when the deck fell down. This is ripped out 11. This explains why it survived and reacted differently than B. B was still attached and inside 12. So what happens when they detension B, when they thought it was okay? Oh, wait a minute. So let's jump back in time to where they had the load testing, if you will, the dead load testing inside the staging area, which I lovingly call the impound, but I can take that back now because I did. So now the staging area, they load tested this there, but the issue is, and I've always had that issue, if you guys recall, I'm always talking about why did they post tension 2 and 11 in the stages they did? Why did they do that? Because I swear it would change all your load forces in the rest of this deal. But I think what they missed is that is that when they load tested it, 2 A and B were in place. But when they put it back into where it finally is resting place on top of the piers, they then detensioned A and B. But they never detensioned A and B in the staging area to load test it for those 40 days, as it was reported by FDOT and also MCM reporting it in their release. So they never load tested it without A and B, with A and B being removed. But yet when they put it in the field in place, they then removed A and B. So the bridge never saw itself without A and B as an applicable force. So when they relieved the compression, anchoring now, I'm not calling it, I'm switching up on terms. The anchoring of B, I believe, acts as an anchor to hold 12 onto this onto the decking, and I'll show you a girder failure basically with when I turn it to the side. So when they relieve that, this was a clamping force. I'm doing this right now with my hands, a clamping force, But imagine this bar doing a clamping force from the canopy down. That when they relieved it, it did number 12, because this is only in 12. This was never connected there. Number 12 being as large as it is, it has a dead weight. It created that downward force, and also here at the top kicked in just a slight bit. A slight bit. I think the joint failed up here slightly. And we don't need much, because I can move maybe 1 inch here and get at the deck. As we look down, we see cracks at the deck on each side of this, on each side of the diaphragm. We see cracks. Let me turn it up this way, where my hand is now, right? So we see cracks across the diaphragm right here, across the bridge deck. This is the top of the bridge decking, going out to the diaphragm. We see it across here. But they're not just flat. So this is a flat plane. If it was a shear crack, if this just had load going down and not a torquing moment, if you will, then the shear crack would be down and not in plane like this. Yet these cracks represent themselves in an upward action like that. They're standing proud, as I showed in the previous video. They're standing proud higher. We're using a tape measure, in fact, it's significantly higher. How do we get that? If this 12 was just going down, if 12 on its own was just sliding down, it would present these cracks as we see, these cracks here, and the cracks here, but all down. How do we get cracks going up? In one of my videos I talked about like a reversal of the forces, you know, sort of a spalling backwards, the symmetry, but now I can simply explain it as the clamping force was released here, and it created a downward torque against this diaphragm that did this, that kicked it out like that. That created a negative moment here of the pier, so the pier probably was flat. And when it did the release of this, and I have this showing you the path pretty much of B coming through, and then the anchor point is somewhere inside here. No magic marker present. Do I? No, none in my pocket. So it would be an anchor. It would look like this. I really want to put the marker on it. So I got a marker right here. Bear with me. And sorry about not editing this video. It just saves me time. Okay, we need to focus. Come on, baby. Tapping the screen, trying to get focus here. I'll come in and let it focus and back out. Fine focus. Fine focus. Okay. It's on autofocus. Great. Let's give it. It needs more contrast. I think we're almost there. Okay, we're going. I know. I apologize. Here we go. So somewhere in there, it would be cap, right? Somewhere in there is the cap. Yeah, it's brilliant, right? We're on the table and blinded by the light. I just saw him, blinded by the light. So somewhere in here is the anchor, and remember this has a dead load on it. That dead load of the entire, and it goes all the way up to the canopy. And it's out there like that. And they post tension through this. I'm sorry, so it looks similar, probably like more like this. All right, this is underneath of the, you'll see the joint. And it's not much, it's probably like that much. Let me see if I can get a profile of that. It's not the full part, I think it's something like that. So that's where also where they run the trumpets. This is where you have your post-tensioning going through this in a radius format, because remember the canopy is curved. But most of that, this little sliver, if you will, would probably be more of the post-tensioning boxing. Gosh, my brain's frozen now. All right, so there's a technical term for the back of it where the post-tensioning caps are and all that when you're framing it out, when you're forming it up. So I'm frozen on that. Perhaps you guys will catch me in the comments on that. So now when they release this clamp force, the downward load, the dead load of this is nothing shy. It's not. It's it's got some quite a few thousand pounds that has to resolve itself by not going down. It has to resolve itself, and what I'm calling now, look at this as a girder. As we look at the end of it, this is a girder system. As we look at, and hopefully I'll do the photograph, but this is the dead load on this girder system. Mid-span, no grout underneath, so the loads create what we're looking at as a shear, the dead loads of 12. Now, some people want to say that, you grab this, that the force that was created to slid this off was the pressure, this load from 12 pushed this off. Well, if the load from 12 pushed, from 11 rather, if it's pushing it off, here's 11. My cats are having a ball in a bag. Okay, you're having a ball with a bag. But the 11, remember this is 11, but 11 has interaction like, I'm putting the deck equal with here. And 11 is, we now know to be still intact, probably all the way, well, you see right here, not probably, pretty much right over to here, that 11 is intact. So here's what they're saying has to slide. This has to slide, that this slides this way and pushes 12 off. Well, how can it slide without moving this joint? How does this slide in that direction without breaking this joint? This can't get longer. It can't get longer. It doesn't, there is no longer force in this. You're releasing the A and B. You're releasing the stresses on them, the clamping force. Doesn't make this go 16 feet longer or 2 foot longer to push this off. It doesn't make it. It doesn't do that. So we release the forces here, but the forces in this are coming across. Remember, this is 10. It has rods coming across. And so right here, I'd have to leave this wedge back in. This has a clamping force holding everything together here. It goes up to the node, goes up into the node area. I guess this would all be node area. So we don't have, we can't get 11 sliding, because 11 looks like this. The best part that you can get that's interacting with 12, sliding it over. I've got to make sure I'm looking, you guys can see it. Even with the deck. Because again, we have images showing that this is in place. And we have the looking down, and you see that they cut it here at OSHA, shows it being, they call it shear. But it didn't shear in failure, as we know here. It was probably sheared by transportation when he did it. But that goes all the way to here. Look what's left. We've got maybe 9 inches of this to shear. But the problem is, this would also still have to move. You just can't grab this 9 inches and say shear. Now, I just want this. We do have splitting in here. But we have no force anymore to only 9 inches to say push off, push off. There is no really, there's no applied force. But then watch this, it's an additive force, additive. So when you release the clamp, the clamping force inside B, this load wants to go down.